Good morning, Andreas. Andreas Bikfalvi. You are a member of the Institut de France. You are head of an INSERM unit you are working on angiogenesis and cancer microenvironment. And you wrote a book on the history of the vessel, on the today scientific research on vessel. And you exposed the general scientific concept on angiogenesis, on vessel physiology and pathology. So why did you write this book, and what was your motivation?
The idea to write this book, in fact, was to give a historical summary about the research that has been done since the ancient times, and also then to summarize that what we know in fact today in the field, and then to draw a little bit the general conclusions of the research that has been done in the field. So and this book is now has been written in French, and it will come out in June 23rd. It should be translated as soon as possible in English. And I will give you now a little talk, a little resume of the work that has been done and has been described here in this book. So this is the global content of the book. First of all, I discuss what is the vasculature. I will talk about historical considerations. I will talk also about evolution. Then where it all began, of course, with Judah Folkman. Then, of course, how the vessels are studied in vitro. The discovery of the first factors that induce angiogenesis. Then there's a whole chapter on VEGF. Then there's a chapter on the inhibition of angiogenesis, because there were some successes and some drawbacks also. Then another chapter is concerned the stimulation of angiogenesis, and then some issues that in fact will change a little bit the initial idea that people had about angiogenesis and about the whole process. And of course I will talk also about lymphoangiogenesis, endothelial cell progenitors and stem cells, the connections with neurons, then some new approaches that target, in fact, the vessels, then what may be the future of angiogenesis, and some philosophical aspects. And I will end with concluding remarks. So in this presentation, I will discuss only 3 points, because otherwise we would hear forever for the whole afternoon. I will talk about historical considerations, because I did really in-depth historical research on the field. Then I will describe shortly some of the issues of our current understanding in vascular development and philosophical aspects derived of the study of the vasculature. First of all, this is the structure of the vascular tree in the circulation. The vasculature is a circulatory system with a small circulation and a large circulation. And it's made of small and large blood vessels. The small blood vessels have pericytes that are attached, in fact, to them, and they have mainly the endothelial cell layer that is the major layer of these cells. However, the larger vessels are composed of 3 layers. That is the endothelial cell layer, there's a smooth muscle cell layer, and the adventous. And of course, we have to say there's a venous component and also arterial component. However, the lymphatic system, we will talk also about lymphatic system. This system is an open system. And it's an open system, there's no circulation. There, for instance, in the skin, you have skin lymphatics. These lymphatics are often structured around blood vessels, and then the lymphatic fluid will be drained in the afferent lymphatic vessels, then go to the lymph nodes, then join in the efferent lymphatic vessels, and then join the general circulation. The structure of these lymphatic vessels is mainly composed by the lymphatic endothelial cell. That is a really specified endothelial cell that has a really specific genetic makeup. There's which drains the lymphatic liquid. There's anchorage filaments also there. There's also lymphatic valves that are there. They're very important for regulating the lymphatic fluid. And there's larger vessels, has also a layer of smooth muscle cells. So that's the basic structure of the lymphatics. And you will see there's specific factors, or more or less, I would say, specific factors, because they are not exclusively specific in the lymphatic and in the arterial and venous system. Historical considerations. When we go back to history, we have, here is a drawing of Leonardo that clearly depicts what they saw at that time about the general organization of the vasculature. There were three spirits: the natural spirit, the vital spirit, and the animal spirit. The natural spirit was taken up by the vessels in the liver. Then that joins, then it went to the heart. Then generally speaking, from the lungs, then came from the lungs into the left heart. The vital spirit is in fact a pneuma that was injected there. In the beginning of this concept, there were no small circulation in the lung described. There was just a straight connection from the lung to the heart. And then all this, the blood from the right heart went to the left heart because there were holes into in the heart, and then it was distributed all over the body, and then it was transformed into flesh. So it was the end stage of this was a transformation into flesh. And all this was an open system because veins and arteries were conducting the blood, in fact, to the tissues. No circulation described at that stage. And Leonardo had also at that time so adhered to this concept and did not revolutionize it. This concept is the Galenic concept that in fact went on until Harvey, and the really revolution of the concept of the blood circulation was done by Harvey. And this is, we can call this the pre-Harveyan phase of the discoveries. There were Gall and Da Vinci, there were the small circulation, even Navis, Serradus, Columbus. And then after Harvey, in fact, people tried more or less to understand how these blood vessels are made of. What is the structure of the vessels, and what is mainly the structure of the very small vessels that are connecting the veins and the arteries. And of course, there were a lot of discoveries: Malpighi, van Leeuwenhoek, Rouge, Hunter mainly, who discovered really angiogenesis at the first time. Schwann, really, who defined the structure of the capillaries. His and Rouget and all the other scientists until the 19th century. So I will discuss just an example of this, and this is the case of Servedus. So Servedus was a quite interesting man. It was a physician, a theologian, and he wrote a book, this very famous book. There are only 3 examples that have been left of this book, called Christianismi Restitutio. And in this book, it was a theological book where he described and he discussed the Trinity, the notion of the Trinity, the role of Jesus, and so forth. And then, when he discussed the notion of the Trinity, and they discussed also how this interacts also with the body, he had to discuss also how the vital spirit is infused and diffused into the body, and it's a pneuma with the lung. And then, of course, there's a whole chapter in this Christianissimi Restitutio where he described this small circulation. It's a very interesting piece of work, and so I recommend to read this. And you can download the book, in fact, easily. It's available. I think Amazon has it. But it's a really big thing, so you should just focus on that aspect, because the other things are so complicated. I mean, it's theology, pure theology, and it's a little bit hard to understand for people that are not versed in theology. So this is the Servetus in the middle that you see here. It was a Spaniard, and he was really against the Trinity. There was in the Reformation. In the 16th century, there was a lot of discussion going on how faith has to be viewed by people. And the Reformation had a lot of ideas, but Servetus was a very, let's say, very strange man, in fact, a very intelligent man, but he wanted to do everything. He wanted to touch on theology, philosophy. He was an assistant of Andreas Vesalius in Paris. Then he left. And then, unfortunately, he got into he sent his book, Christianisme Restitutio, to John Calvin. And John Calvin was the major Protestant leader in Geneva at that time, had a huge influence in Europe. And it was totally against the ideas of Calvin. And at the end, Servetus unfortunately went to Geneva to meet Calvin, but he was arrested and burned on the stake with his books. It was a very difficult time, but he had also some of the defenders on the who is on the left side of this slide. Castellion, he was a very, very famous person, and he went really against against these ideas, against the burning of the stake of Servetus, but he was unfortunately not read at his times, and his ideas did not went through. They came even through 100 years later only. So, and this is in the 19th century, a writer wrote this. I mean, people who know French can read this. That in fact, Calvin has burnt on the stake Servetus only by jealousy. So it's let's say it's a pretty, it was a pretty sad story. So then came William Harvey. And William Harvey is very important because he wrote this famous book, Exertatio Anatomica de Motu Cordis et Sanguinis in Animalibus. And he really defined the circulation. And already before the publication of his book, he gave talks. And in one talk, April 17, 1616, he already described the organization of the circulatory system. And let's see, when we cite Harvey in chapter 1 of his book, when I gave my mind to vivisection as a means of discovering the motion and use of the heart, I sought to discover these from actual inspection and not from writings of the other. I found the task truly so arduous, so full of difficulties, that I almost tempted to think with Factorius that the motion of the heart was only comprehended by God. So it was really for him a undaunted task to, do this and to tackle this. But he did he went totally away from the classical way of thinking, just to read the books of the elder, and then to reinterpret the findings with them. But he said, no way, I will learn it myself. And he did all the experiments, even on several species like fish, snake, and dogs. Of course, with today's standards, very cruel. But where he interrupted the flow and so forth, he did a number of experiments, and he really could show that there's a recirculation going on. Another later, very later, on 1846 and 1848, the structure of the small vessels, capillaries, was in fact really established, or let's say was described the first time. Even at that time there were hot debate on that. And Schwann, who described the cell theory, he, in his drawing that you can see on this slide, really envisioned two cells, one internal cell and one external cell, that you see clearly in this book. And of course, he interpreted that finding that the cells belong to the vessel wall, but he did not really distinguish both of them. Of course, another explanation would be that they are, in fact, outside tissue that are just growing in. But to our standards, to our understandings now, one is, in fact, the endothelium, and the other, the accessory cells. So the thing is that is the first, to my mind, I found this, it's the first description of the structure of the vessels. And this has been a hot debate, and this hot debate went even on in the 19th century. In the 19th century, still people like Earle thought between the veins and the arteries, the capillaries were only there without any wall. Where just the blood was circulating, that's it. Then afterwards, several of the scientists of that time saw or thought of a membrane, then afterwards of a cell, and then afterwards also of accessory cells that are on the tube. So, and this has changed during times, and there were mainly two theories also that were in conjunction with these discoveries. This is the blastema theory and the corpuscular theory. So the blastema theory at the beginning did not really said that we can have a wall, we can have a membrane, because there will be only fluid will be transferred. And fluid can transfer membranes. Opposite, the corpuscular theory at the beginning really stated that it's excluded that membranes are there because solid material and cells can be transferred across the vessel. And that, of course, has evolved afterwards in time. And people really came up and found out that really there was a precise structure of the vessels there, and that even solid material can cross these vessels. So then the parasite, discovery of the parasite is accessory cells. Rouget, Zimmermann, and Meyer. So you see here the nice drawing that Rouget did here, where you see them on the vessel here. So when we summarize the concept in function of time, Galen, there were first the Galenic concept, where the pneuma went through the arteries, and the blood of course, mainly the blood that will become flesh, I have to say, mainly through the veins. Then came Harvey with the circulation, but the connection of both has not been established at that time. Then Malpigny van Euvenlock, who established that there were a connection, and how these connections are made of, Schwann, van Recklinghausen, and Heath. So this is the evolution of the concept that went through. Now, discovery of angiogenesis. So discovery of angiogenesis, there's one famous surgeon, John Hunter. John Hunter was really a very remarkable figure because he did all kinds of things. He did anthropology, he did primatology. So he was an incredible man. A surgeon, physician, and he did the most of the dissections of bodies in his century. So that was really, he had a huge interaction with grave diggers. So he was really, and he got a lot of bodies to dissect. He had he has built for himself a whole lab institute in London. So when he came on angiogenesis because of the following. There were the coach drivers. The coach drivers had boots, and these boots were hurting their ankles. And it gave rise to aneurysma, a big aneurysma. And usually at that times, what they did, people were sent in the hospital, get amputated, and died. And John Hunter thought that, in fact, we could do something else. We could ligate the femoral artery at some height, and then maybe the blood will find its way around the obstacle. And he did, first of course, experiments in animals, what they did all the time, and then he applied this to one of the coach drivers. And here's the coach drivers on the left. Should only look. This is the aneurysma of the coach driver that he got out. So when he said to the guy, to this coach driver, when you die, you give me your body. That was the deal. So I will operate you, but you give me your body when you die. And then he injected, of course, his some of the dyes that were mixed with oil and wax and so forth. And then he could really see around this obstacle, around the ligation, that there were new blood vessels formed. Okay, so that's the first. And he coined this word angiogenesis, in fact. Now, with cancer, the idea that blood vessels play a role in cancer came, in fact, from Karl Tirsch. Karl Tirsch was a German professor at the University of Erlangen in Germany, and he did research, and he wrote a book. It's called the Epithelialkrebs, namentlich der Haut, mit Atlas. So it's let's say it's a book on the structure of these epithelial tumors, and there he really realized that the epithelium, that the tumor epithelium is dependent on the stroma, like a plant from the soil, and the soil need to bring substances to the plant that really helps the growth of the tumor. It's a very beautiful German, so it's very hard to translate because this German there is very beautiful. So I'm not able to translate this in a good English, but I mean it's basically the sense of his statement. This is this book. And then came Ernest Goldman. Ernest Goldman was a professor from the University of Freiburg, and a lot of people think and cited him wrongly, because Goldman is cited usually by a lot of scientists with one N, even Judah Folkman. And in fact, people think that he's an Englishman, but in fact he's not. He published all his papers in English journals, or a lot of papers in English journals. But he was a professor at the University of Freiburg, and his name is written with 2 N. What is really clear and astonishing in his work. Maybe I will find the citation here. So he published this in Lancet in the Royal Academy of Medicine. So what he saw, and he did a lot of experiments, that the normal blood vessels of the organ in which the tumor is developing are disturbed by aortic growth. There's dilatation and spiraling of affected vessels, marked a capillary budding, and new vessel formation, particularly in the advancing borders. So that was, and he did all his experiments afterwards in animals and man. So what he did was he injected bismuth oil, and he did X-rays. Okay, so at that time X-rays was a little bit, was not as standardized as now. And here, for instance, you have patient cancers, stomach cancer and liver, where he did this experiment. And where he sees that, okay, he's not able to see these very small vessels here, but he sees at least that these vessels are converging, in fact, to the tumor. So his interpretation of this finding was very, at that time, when I read this first time, strange, because I regard the vascular, he said, quote, I regard the vascular neoformation as a standard by which we may test the body's power of reacting against the tumor, the malignant tumor. So that means for him, it was a kind of rescue reaction against the tumor. And it was an insufficient rescue reaction, because the tumor still was able to grow. I think this is a very interesting point, and we will discuss this later when we discuss the problems with the anti-angiogenesis treatments. And now a big leap forward with Judah Folkman. So this is, I think, really the crucial step and crucial idea in angiogenesis, because he formulated the conceptual framework in which for years to come a lot of research has been conducted. So first he coined the name of highly integrated ecosystem. Then he posed as a kind of dogma that tumors are absolutely required to attract blood vessels for growth. Then also he stated that the dormancy state of tumors is due to the absence of vascular growth, and that the tumors are producing actively factors that attract blood vessels, the famous tumor angiogenesis factors. And tumor development can be halted and dormancy induced through anti-angiogenesis treatment. So this was really the conceptual framework for years to come, and a lot of science that has been done has been produced in this conceptual framework. So this is the drawing of his one of his papers in 71, where really he sees the TAF as the really organizing principle of the tumor angiogenesis and also of the growth of the tumor. So when we summarize a little bit what we have said or what we haven't said, because a lot of other scientists that have been contributed to that idea has not been cited in this presentation, like Clark, Ide, Greene, Algier, Mervyn, Algier, Greenblatt, and so forth. We can say that all these people have contributed really to the concept, but really a workable concept has been proposed by Folkman in '71, which has been the guiding line and strategy for a lot of scientists in the following years. And the evolution since 1975, so purification of angiogenesis inhibitors, then discovery of VEGF, of course, then the blockade of VEGF that can block tumor growth, vascular targeting, the identification of lymphangiogenic factors, the concept of endogenous angiogenesis inhibitors, even that this concept is now a little bit under attack, vessel cooption, vascular guidance factors, tip cells, and so forth. Just a few words on lymphatics. So lymphatic were first described by Azelli, and then, of course, John Hunter also described a lot of lymphatics, and especially one of his students, William Hewson. So William Hewson said for the lymphatics, the lymphatic vessels are small tubes that have now been discovered in most parts of the human body. The fluids that they contain is generally colorless as water, a circumstance which procured them the first name ductus quasi, and afterwards of vasa lymphatica. Of course, the lymph, like that of the child, is from extreme parts of the body, it's from extreme part of the body to the center, and the lymphatic vessels lie close to the large blood vessels. So that's really a very, very nice, nice description of the lymphatic system. But however, the idea how this lymphatic system was formed and developed was not clear, and a lot of people thought it came from the tissues and not from the veins. And Florence Sabin was the first in 1904 really to describe the centrifugal theory of lymphatic formation. So what she did is she had pigs, and in the venous cisterna she injected ink, and then she injected that in several time intervals, and then she followed this with time. And then, of course, she could evidence that this extend more and more, let's say for the skin lymphatics that are shown here. And, of course, this proves really that the lymphatics are originating from the veins. So what she says, quote, at the first, the lymphatics were thought to begin in wide mouths of walls of the various cavities of the body, and then as these openings proved difficult to find, attention became focused on the lymphatics in relation to the tissues. The theory which I hold is that lymphatics arise from the endothelium of the veins and growth by multiplication of endothelial cells. So that's the total break with the concept of her time. Of course, now some recent papers just came out this year, I think, or at the end of last year, that see to some extent some lymphatics can be originated also from the tissues, from the periphery. But the major part, at least, of lymphatics is generated from the veins. Current concepts. So what we have is, first of all, we clearly see that we have angiogenic factors and gradients that stimulate the sprouting of the vessels. Then there will be a selection of tube-forming cells, the formation of the sprout. Then vessel guidance factors will intervene. Matrix degradation will occur. Branching will occur. Lumen formation will occur. And establishment of all the connections and flow will finally be achieved. And what we know now is listed here a little bit. So we have a lot of issues. For instance, the guidance tip cells have been identified and characterized. The formation of the vascular lumen to some extent, even if it's not complete, has been characterized. Vascular cooption, the neuronal connections, vessel guiding, pruning, and so forth has been characterized. Normalization of blood vessels has also been characterized. Vessel permeability, metabolism, the angiogenic switch also, and the EPCs. We will discuss this a little bit later, and the downfall, because the EPCs were a hot topic for until recent years, but there was a downfall from the EPCs. There's a revision also of the initial Folkman idea, at least in the context of tumor angiogenesis and clinical relevance and significance of angiogenesis. And for the lymphatics, there are a lot of lymphatic factors, actors, intracellular molecules, transcription factor has been uncovered. Lymphatic development, recent studies has been really contributed to elucidate more of what's happened, the formation of the lymphatic valves and the role of lymphatics and lymphangiogenosis in disease. With tip cells and stalk cells. So this concept is a crucial concept. It's in fact a little bit derived from the nervous system, a little bit similar to it, that you have, instead of the growth cone in an axon, you have a tip cell that will send out his extensions, and you can see here. And in this extension, of course, you have a lot of receptors, like VEGF receptors. You have also receptor guidance factors that are there. And then you have also stalk cells that come a little bit later, and there's a whole system with Notch and delta and FGFs and VEGF and all this. It's an integrated system which will regulate the maintenance, sprouting and maintenance of this tube. So all this is described in detail also in this book. Normalization of blood vessels. This is, so I highlight here now is just some of the aspects. I don't discuss everything because everything is discussed in detail in the book. I highlight just some. I do just some snapshots on what is described in the book. So vessel normalization. The initial idea was that in fact anti-angiogenesis will destroy vessels and will starve the tumor. And in fact, Rakesh Jain has proposed another theory that in fact the vessel structure through angiogenesis will return to a normal state, and this will allow to in fact increase blood flow and allow chemotherapy and other treatments to arrive easier to the tissue. And this is also in connection, so this is not yet 100% accepted by some of the scientists, but this is also in connection with the relationship of the endothelium, the vascular tube, and also the pericytes, because in the vessel, in the normal vessel, the pericyte endothelial connection is tight. In the abnormal vessel, tumor vessels is loose, and again after normalization, it is again tight. So it's in connection with this process. Revision of the initial Folkman paradigm or concept. There are some tumors that may acquire independent growth of vessels. That what we know, at least also under treatment. There are also some, for instance, some gliomas that have mainly an infiltrative phenotype, and they only use pre-existing blood vessels. So the concept is not per se 100% correct, even though that most of the tumors have an angiogenic switch. The other issue is that anti-angiogenesis therapy did not live up to its expectations. That means that progression-free survival in most of the tumors is improved, but overall survival is not, and that's the problem. Third point is the evasive resistance, that under some extent anti-angiogenic treatment can induce evasive resistance. That means the tumor can escape from its invasion and can become even more resistant and angiogenesis independent. And of course, all this needs, it works well in some, anti-angiogenesis works well in some patient groups, in some tumor groups. It works well, of course, in eye disease, where we have the, in eye disease, when you have neoangiogenesis in the eye, retinopathy, and all this kind of thing. So in the eye, neoangiogenesis in the eye, that treatment works pretty well. But in tumors, it's a problem. It has been a little bit problematic, even though in patient subgroups it works. And of course, it needs to identify suitable biomarkers for this. So one example still is renal cell carcinoma. So renal cell carcinoma, still in renal cell carcinoma, anti-angiogenesis, that means TKIs, that means like Sutent. Of course, Sutent is more larger. It will also tackle other factors like FGF and so forth, but it's a high, these molecules are often high inhibitors of VEGF. And they are still first-line treatment in renal cell carcinoma after immunotherapy. The immunotherapy, this new immunotherapy with PDL1 antibodies, like this is what we call TCCI therapy, is important, but still TKIs, they still stay in the first line of this. Even though there's been a recent paper that after resistance to TCCI, that means to PDL1 inhibition, some of the TKI inhibitors may still work. So it's the question is not yet really settled, at least in renal cell carcinoma, where Tim Eisen wrote this review, tyrosine kinase inhibitors in renal cell cancer, losing an empire and yet to find a role. So maybe the empire of these treatments, TKIs and anti-angiogenesis, is a little bit lost or not more as important as it was, but at least they have a role. The other idea is, in the revision of the Folkman idea and paradigm, is that in fact what counts is maybe not the reduction total number or reduction of blood vessels, but the quality of the vessels. And there has been a very interesting study by Jean-Philippe Girard, who is in Toulouse, and he worked on the high endothelial cell venules and in relation with the immune system. So these high endothelial cell venules are very important in triggering specific immune cell subtypes that will kill the tumor. It's a very, so you should look up his papers, they're really interesting, and some other scientists now really, like Gabriele Bergers and all, they're going also, I mean, into this direction. Maybe the quality of vessels is important and not the quantity, and the interaction with the immune system is important. So which vessels can really guide and conduct the specific immune cells that may kill the tumor. Maybe there's a research field, a really research field to do how this interaction with the immune cells and the vessels is occurring and what is doing in tumor angiogenesis. The role of lymphatics in the dissemination. So there's, in fact, the initial idea of the lymphatics was the lymphatics were never inside the tumor but always outside. And Michael Detmar has shown clearly that this is not the case, that you have intra-tumor lymphatics. And they may also trigger the immune cells, of course, interstitial fluid, and will take up the immune cells. But they may also send out soluble factors that will travel along the lymphatic vessels, like VEGFs, VEGF-C, and that may prime the lymph nodes already for seeding. So that's a really interesting idea that the lymphatic system can be primed to some extent to accept, in fact, the tumor cells. So this is another aspect that is also discussed in the book. Now I come to this issue that has been hotly debated for some time. It's already some time ago. This paper came out in 2008, where Puronen really killed nearly a whole field. Okay, because in this they did really re-evaluate all the roles of the endothelial cells, so-called endothelial cell progenitors, in angiogenesis and especially in tumor growth. And of course, this has been led to a reply by the major actors in the EPC field, like Rafi and Jeffrey Leiden, and all the people who signed this paper. So really, I mean, it was a kind of very, very strong and aggressive statement against this work. I mean, if I recommend to read this, let's say, everybody, and to see how harsh a scientific debate can even become. So it's very hard. It's like to play a game with, to do a fist fight, right? It's very, very, very strange. So it was a debate, but nevertheless, this one paper really nearly stopped the whole field. So you will have very few meetings now where people talk, or really no one will talk anymore about the role of EPCs in tumor angiogenesis. That's really, that's science, you know. Sometimes you need 50, 100 papers against one, and one paper will really destroy everything. So, and how science can really go, in fact. So some of the philosophical aspects derived of the study of the vasculature. So what has been created is a shift of the paradigm. That's really how a paradigm can shift, how a conceptual framework can shift, and what happens in this respect in vascular biology. Then the interaction between fields and cross-fertilization of domains. Then the impact of leaps, of advances, of innovation, of technology. Then evolutionary concepts. Then vessel geometry and the morphogenic principles that underlying this, blood vessel function. And similarities and connections between different biological systems. And approaches, general approaches, scientific approaches in terms of philosophy of science. So when we look on the first point, the shift, in fact, the shift, in fact, of the paradigms. What is a paradigm? When you look up Kuhn, that has been published, this is the 3rd edition of his book, The Structure of Scientific Revolutions, in 1996. It's an universal recognized scientific achievement that for a time provides a model for problems and solutions of a community of practitioners. So, of course, Kuhn has a relativistic stand. That's the only problem that scientists may have with Kuhn, because he's a relativist. That means the accomplishment of science and the inventions, findings are only for a certain given time and can be succeeded afterwards. And there's not really a permanent thing, you know. It would be, if you would think that a circulatory system can be subset by another system, you should show me. But that's in fact the idea of some of these philosophers that have often pretty abstract ideas that are not bound to reality. But when you look on the paradigms that you can identify here, you have, I listed a number of them here, smaller ones and larger ones. The big ones is, of course, the circulatory system in vertebrates. But then, for instance, there are smaller paradigms that are, for instance, angiogenic factors have a vascular specificity. So people went into the concepts they did. We look for factors that have a vascular specificity. It's very important to look at them. And of course they found them, because at that time there were FGFs and so forth, and FGFs were broad range factors. They hit all kinds of cells, and people thought we need a specific vasculogenic or angiogenic factor. And in fact, this program was so strong that in fact it drove people to the discovery of VEGF, which was thought to be a specific angiogenic factors, at least at the beginning screening of all these factors. It was a specific, claimed specific factors. Of course, it's not true. There are VEGF receptors in a lot of other tissues, in lytic cells, in the nervous systems, in the, let's say, they're all around. So, but at that time, it was not known, at least the screening on in vitro in cells did not show anything. So people thought really specific, it was specific. So the whole program went on a false idea. So this is just an example that I will cite, so everything is described more in detail into the book. After, another aspect is the interaction between different domains. If angiogenesis would not have gone through the cancer field, at least angiogenesis factors would not have been discovered in that time frame, because tumors are extremely rich on angiogenesis factors. And in fact, it was from the study of tumors that the factors have been discovered, the general idea has been laid down, and this went afterwards into all other fields. It was absorbed into cardiovascular, neurovascular eye disease, and inflammatory disease, and also in other areas of biology. So it's just to see how important is at one moment to have a field that in fact at the beginning was not inclined to study the specific topic, but who laid down the conditions to discover factors and to make a major leap in the discovery of factors that are important in another system. The other is technological leaps in angiogenesis research. Of course, hunter injection of dyes. All this was done to visualize the circulatory systems. But a major technological leap was done by the discovery of heparincephalose chromatography. Because heparincephalose chromatography, angiogenesis factors have high affinity for heparincephalose and are heparin-binding growth factors. And due to this affinity, these factors could have were identified and sequenced, because at that time we had not this sophisticated cloning and what we have now. So it's important. Another leap, very important leap, and I cite only the specific ones, is the culture of vascular cells, endothelial cells and the pericytes and so forth. Because this allowed us to study signaling, to study behavior features of these cells, and to discover a lot of things that's going on in the vascular cell and in interaction with other cell types. Evolutionary considerations. So what is clear, that the endothelium has emerged around 500 million years, and that in fact it was with the last ancestor of the vertebrates. So it's a pretty old tissue, in fact, in evolution. Or you can say old or recent. I don't know if 500 millions is recent or old in terms of the lifespan of the universe. It's really recent, but in the lifespan of the living systems is, I would say, intermediate. One idea is really important, that you have a distinction of invertebrates and vertebrates. And in vertebrates you have no endothelium. You may have a closed circulatory system, often also an open circulatory system, but there's no endothelium. And the vessels, what they call the vessels that even are conducting fluid and also cells, are made by epithelial cells. And these epithelial cells are, in fact, with the interaction of the fluid phase, have a matrix. So the matrix is exposed to the fluid phase. So one can imagine what's happened if in a normal vertebrate vessel, you expose the matrix, you do an abrasion of the endothelium, you expose the matrix. What's happened? It will produce a clot. Will be thrombosis will be induced. But this is not at all the case here. So, and then of course you have. This is just an example of an organism that is Botrytis schlosseri. It's in the Atlantic Ocean. It's near to the coast. In the Atlantic Ocean, it's a zooid that is made by a number of small individuals that are in fact here, and that are in fact all connected via membrane. Okay, and they are linked together by a vascular network, tubes, so all around. You can even have Botrytis, one in green and one in red, and make them in connections. They will fuse, and the vessels will fuse. So it's really fusion going on. And what is very interesting is that they have VEGF receptors. They have in the epithelium, they have VEGF receptors. So they have the kind of VEGF receptor that is so they have one type of VEGF receptor here. That's very strange. The ligand has not been found up to now in this species. So again, here you have what I said before. You have in invertebrates, you have the You have this epithelium, the mesothelial cells, they call them also like this. I mean, it's in fact epithelial cells. And they have a lumen, the lumen is there, and the lumen is exposed with the matrix that you have here. Here's the matrix. Whereas in the endothelial cells, you have in the vertebrate, in the lumen, you have the endothelial cells here. Okay, so the structure is very different. And it has been, it's been studied in lobsters, in worms, and in fact in Amphioxus, it's the first animal where you have an endothelialization of the vessels here with endothelial cells. So it's not yet clear where the endothelium cell is derived from. Two theories: it's from the hemocytes, from circulating cells, because circulating cells, hemocytes, I mean invertebrates, have VEGF receptors. And they may also adhere to the matrix and in fact form the endothelium. So this is one of the theory that. The other theory is, of course, a cross differentiation from the epithelium, from the epithelial tubes. So in the vertebrate, the central organizing module of the vessel is the endothelium. Everything is built around the endothelium. So, and it has in fact co-opted the oxygenation function for the tissues. And another aspect in this development issue is that there's this notion of network kernel. So what's that? It's a regulatory node or module similar in different species, the general function, with the same general function. So it may be replaced. For instance, branching morphogenesis in Drosophila. In the tracheal system, you have FGF, notch, and delta. Whereas in the vertebrate vascular system, which has taken up in part the oxygenation function of the Drosophila tracheal system, you have VEGF, notch, and delta. So that is when you compare vertebrates and Drosophila, I did that here. So there's a guidance cell, of course. There's oxygen sensors. There are soluble factors. There are factors involved in cell interactions. And in vertebrates, the tissue are the blood vessels, and in Drosophila, it's the tracheal system. So it's just a transposition of the function with the same regulatory factors, modules, that are in fact just transposed and exchanged. Now, finally, what are the approaches that vascular biology and biology in general is using? You can have inductive inference, you can have the deductive inference. You have, of course, the verification and the falsification principles. Bayesian statistics is used. The error statistical method is compatible with this, and the inference of the best explanation. So all these issues are really explained in the book, and you can also go on the website of Marcel Weber, who wrote a whole section on what are the methods in biology, in experimental biology, and he describes all these issues that are in fact on the slides. But just to say that, often biologists use inductive inference. This is the mainly thing that drives biology, and the verification principle. And the falsification principles are not so much used, because it's more important, even if you train your students, to say to them, look, you should design experiments that will destroy your hypothesis. Design them, do that. Try to design experiments. Can you destroy your hypothesis? And if the hypothesis stands, then your theory is much stronger. Of course, you have to do this with care, because sometimes you can destroy a good hypothesis with very stringent experiments, and in fact you will fail also. So it's a kind of, you have to have that on the fingertips to some extent. So the final word I will leave to William Harvey. So this is in Latin here, Fondus verum istu tracto collegii amantissimi. I will not read this in Latin, but I have the English translation. My dear colleagues, I had no purpose to swell this treatise into a large volume by quoting the names and writings of anatomists, or to make a parade of strength of my memory, the extent of my reading and the amount of my pains. Because I profess both to learn and to teach anatomy not from the books but from dissections, not from the positions of the philosophers but from the fabric of nature. And then because I do not think it's right or proper to strive to take from the ancient any honor that is their due, nor yet to dispute with the moderns and to enter in controversy with those who have excelled in anatomy and been my teachers. I would not charge with willful falsehood anyone who was sincerely anxious for truth, nor laid to anyone's door as a crime that he had fallen into error. I avow myself the partisan of truth alone. I can indeed say that I have used all my endeavors, bestowed my pains, on an attempt to produce something that should be agreeable for the good, profitable for the land, and useful for the letters. Farewell, most worthy doctors, and think kindly of your anatomist. William Harvey. Thank you very much.
Thank you, Andreas, for this wonderful overview of your book, and we're eager to read it when it's out. So what has been which part of the story was the most difficult to write for you?
I mean, let's say the most easiest part was the science part, because the science part we are doing it all day, and we know we go to all the meetings and we know what's going on in the field. Of course, the historical part has required a lot of research, because the thing is that I did not want to just get on the secondary papers. I wanted to get a lot of the original, even though I took some of the secondary too. You cannot do without. But I took really, for instance, Schwann and all these guys, I read them in original. So I have it was really, I mean, it was a task, and to get all the publications and all this, my file is full for like that. So this was, let's say, a big task. Yeah. The other was also to articulate this well, to make it more understandable for same time scientists and for people of the general public, that even if they do not understand everything on that they at least understand really the principles and the issues, what's going on, to make an interesting story, and not to write a hyper-academic book, to make it interesting and not chapter 1, chapter 2, chapter 3, all this what we know from the academia. And I think, I don't know if I succeeded, so up to now the feedbacks that I got were pretty good, but I let judge the reader for this.
So which part was the most exciting part to write for you?
The most exciting was the historical and philosophical part, because the science I know. So it was, of course I have excitement in science, but also to think about the concepts. What is the essence of what we are doing, in fact? Where we go, what we are doing, where we came from, and where we want to go, and what are the issues. So that's, I think, the most challenging. to have really this kind of laid-back attitude to vision things with more wisdom, I would say.
And what would be the, in this short period of the vessel, what would be the crucial periods and the turning points of the vessel story, if you have 2 or 3 turning points of the...
From the past or for the future?
No, for the past.
The crucial turning points are in fact the discovery of the circulatory system that we know it's Harvey. Without Harvey discovery we would not be there. Then another crucial point is really the cell theory. I think that how the vessels are made up, what is the structure even of these small vessels of so that is in fact not just the matrix around there where the liquid is flowing between the veins and the arteries, but there really is organized structures, organized principles. So that I think it's very important. The third part is very important, that is the discovery that it's not a static system, that the vessels can develop, can be formed. It's not just laid down one and forever, but it can evolve even during the lifetime of an individual. That's, I think, it's very important. The other thing is the elucidation of all the factors and the regulatory systems that underlie this process. So I would say this 4 or 5 are very important.
Should we be disappointed by the results of clinical trial with anti- or pro-angiogenic therapy?
Yes and no. I would say yes, because of course, people had great expectations when they saw the first data from the Hurwitz paper in 2004, where he showed with Avastin an increase, in fact, in progression-free survival in patients and cancer patients. So that was a huge, because normally people think progression-free survival, overall survival will follow. But this, unfortunately, in most tumors has not stand up as scrutiny. Okay, there are patients that, of course, can be, they respond extremely well to anti-angiogenic therapy. But at a large scale, when you line up the numbers, it will not translate into overall survival. So this is, I'm disappointed, at least for the cancer field. I'm not disappointed for eye disease. There, I think it's pretty clear that works pretty well. And for the cardiovascular disease, at least the injection of factors, let's say like FGF and VEGF globally, was a little failure. So it did not, all the clinical trials that have been done, for instance, on plasmid FGF or recombinant proteins, stuff like this, have not been, at least at large scale. With small numbers, they showed some nice effects, but with large scale, they didn't show up. But there has been, of course, the idea of, let's say, of cell therapy, and maybe some of the progenitor cells can be used even as triggers for, or as loads of angiogenesis factors. And there's been studies with this. They show little promising results. So it's not so unfortunate in cardiovascular than in the tumor. But I think in the tumor we may have an issue with immunotherapy and anti-angiogenesis, I think. So the thing is that maybe to combine them, how to combine them, how to do that, and maybe also to do more research, because I think the angiogenesis phenomenon is a very important phenomenon in tumors. It does not mean that if clinical, up to now clinical results are not at the expectations that we had, that this is not something that should be pursued, because it's, I think there still is very important things to discover, especially I think the interaction with the immune system and with the quality of vessels, the change of the quality of vessels. So it's not, of course, you can say the pharmaceutical industry, they are less interested now in in targeted therapy on the VEGF system and our system, but I don't think that they are absolutely right. I mean, you know, there's all times a hype and a hope, and with immunotherapy it's now the same. You have a hype and there will be also a little downfall, and we will see how all these therapies will at the end combining themselves.
So you see the future of the angiogenesis or the treatment for angiogenesis more to associate this treatment with other treatment, not see the angiogenesis as the main.
No, I think it's an association, and the good and the right association has still to be discovered, and the right molecules too, because people are hitting. The pharmaceutical industry is often interested in the more fancy stuff, fancy targets, and sometimes, I mean, they fail. They fail enormously. So I think we have to find the right combination to target vessels, and I think it may still have a role. And in fact, if you look in the kidney, some of the tyrosine kinase inhibitors in patients are working in several subgroups of patients, and they're still first line. Okay, so it's not so bad. It's bad, but it's not so bad, and I think we may have hope at the end.
Okay, so if you had to write not the story of the vessel, but the future of the vessel, what would be your,
what would be my
guess or your
future
dream?
Future of the vessels? I mean, there will be. I mean, of course, we have talked about angiogenesis, but we can talk also about building vessels. That would be, I mean, the whole approaches of making artificial vessels. I think that's also it's this whole area subject that is pretty interesting, and may become also very hot in regeneration of tissues and so forth. And the other things we will see, I mean, there will be, for instance, improvement in the treatment of several eye diseases. There will be, hopefully, improvement of some strategies that even can be combined with in tumors with other treatments, immunotherapy and so forth. We have to find the right combinations. So I think the way to go would be there. We are not yet at the end. No. Okay.
Thank you, Andreas.